So this is another question from WAHEC 2006 and some other years. So a solution of this, that's the question on the board. So calculate the mass of the copper of the cathode after the experiment. Mass of copper deposited at the cathode. Still remember the equation is equals to decrease in mass of copper anode, or is equals to increase in mass of copper cathode. That's the equation. So what is decrease in mass here? So decrease in mass of copper anode, it will be mass of copper anode before is equals to mass of copper anode before experiment minus mass of copper anode after the experiment. So it will be 7.20 minus 4.00. So we subtract this one will give you 3.20 gram. That's the mass of the substance deposited of copper deposited at the cathode, centered as increase in mass. Note this answer. Increase in mass of cathode, increase mass of copper cathode is written as a decrease in mass of copper anode. This equation. So is equals to mass of copper anode cathode. That is after minus mass of copper cathode before. So increase in mass is written as 3.2 is equals to mass of copper cathode after. From the calculate the mass of the cathode after. This is what we don't know. Let me call it X minus mass of copper cathode before. So I will give it mass of copper cathode before the experiment 5.75. So 5.75. So it will be X time is equal to 5.75 minus 3.2. X now will now be 2.3 here to 2 here is 2.55. That is a gram. So that's the answer. That is Roman figure 1. Roman figure 2. If the electrolysis was carried out for 1 hour, time is equal to 1 hour. That is 3,600 seconds. Convert to second. This 20 minutes. Okay, 1 hour is equal to that. 20 minutes is equal to 20 times 60. That is seconds. So this time that is 1,200 seconds. So T now will now be 3,600 plus 1,200. So 4,800. 800 seconds. That's the total time in seconds. The current is going to be 2.0 ampere. So Q is equals to IT, which is equals to I 2 times T. That is 4,800. So this one will be 00. It will be 00. This one will be 6. This will be 96,000. 9,600 coulombs of electricity. This is Faraday. Remember, we are coming to that. 96,500 coulomb is equivalent to 1 Faraday. Therefore, 9,600 coulombs equivalent to 9600 all over 96,500. When you divide this, will now give you in Faraday. That's the number of Faraday. Divide this cancel this. So you use your calculator to achieve 965, whatever you get in Farad. So we have converted it from coulomb to Faraday. So 96,500 coulomb is equal to 1 Faraday. So we have gotten 9,600 coulomb. That is what we have to do. Faraday. Let's see the meaning of Faraday. 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 This is the quantity. This is the quantity of electricity required to deposit 1 mole of a monovalent element. 1 mole of a monovalent element. Meaning 1 Faraday of electricity, 1F, is same thing as 96,500 coulomb. So that is the relation between Faraday and the coulomb. 1 Faraday is equals to 1, meaning 1 F is equals to 96500 coulomb. Please take note of that. That's Faraday. So we normally have calculations here. So let's start with int. Int number 1, or A. Int A. Let's see monovalent elements. Monovalent elements. E.g. sodium is monovalent, potassium monovalent, and etc. etc. is what we mean by monovalent. So 1 mole of a monovalent element requires 1 Faraday. 1 Faraday. Take note of that. 1 mole of a monovalent element is equal to 1 Faraday. And 1 mole of monovalent element is equivalent to the mass number. So atomic mass. So 1 mole of a monovalent element is equivalent to its atomic mass. Equals to its atomic mass. So therefore we can say 1 Faraday is required to deposit the atomic mass of a monovalent element. e.g. for sodium now, mass number is 23. It means 23 gram of sodium will to be deposited by 1 Faraday because it's monovalent, or 1 mole of sodium. 1 mole of sodium is deposited using 1 Faraday of electricity. Please take note of that. That's what this one is saying. So let's see example 1 here on int 1. Int number 1, example 1. Calculate the number of Faradays required to deposit 2.3 grams of sodium. Take sodium, mass number of 23. So you know the question is between mass and Faraday. So you take between mass and Faraday. So by stating that 23 grams of sodium is deposited by 1 Faraday. Therefore, 2.3 grams of sodium. Let's see the number of Faraday. The 2.3 times 1 divided by 23. So it will be 0.1 Faraday. 0.1 Faraday. If they don't leave the unit of farad, they can leave it in coulomb. So if you like, remember that 1 Faraday is 96500 then in coulomb. So this one will be 9650 coulomb. Either you leave it like this or you leave it like this. It's still the same thing. That is example 1. Example 2. How many Faradays of electricity is required to deposit 0.5 mole of potassium. To deposit of potassium. This is another question. How many Faraday of electricity is required to deposit 0.5 mole of potassium? I will say 1 mole of potassium require 1 Faraday because it's a monovalent element. So therefore 0.5 mole will give 0.5 times 1 divided by 1. So to give is 0.5 Faraday. So you can convert this to a coulomb by multiplying by 96,500. That one is settled. So example 3. How many grams of sodium will be deposited by passing 3 Faraday of electricity. So take sodium to be 23 grams. So from our equation, remember 1 Faraday is required to deposit 23 grams of sodium. That is what you know. Then if you now pass 3 Faraday, it will be 3 times 23 all over 1. So this one will be 69 gram of sodium will be deposited. Please take note of that. So example 4. Calculate the mass of sodium that will be deposited by passing 9,600 coulomb of electricity. So you know 1 Faraday is required to deposit 23 grams of sodium, and this 1 Faraday is equivalent to 966,500 coulomb will deposit 23 grams of sodium. So therefore we are given 9,650 coulomb. We give 9650 times 23 divided by times 23, everything divided by 96500. So when you do this, you are going to get 2.3. So the answer will be 2.3 gram. Please take note of that. The answer will be 2.3 gram. Multiply this by this, divide it by this, we give you 2.3 gram. So we are giving you 4 good examples